All right. Good morning, everyone. I hope everybody had a great weekend. So how many people saw the email I sent out about me taking a personal day on the 20th? Start with that.
Yes.
I
Yes,
saw
I
it. Good with me.
That's good with you.
did.
Okay, that's fine. So I updated the course syllabus just a little bit. So if you go into the outline and overview, I have a new schedule here. So I just wanted to talk about what will happen. So we're here in week 5. Wow, this semester's going quick already. Don't you guys feel? Actually,
Yeah.
Yep.
it's great. It's great. Um, so next week, what I'll do, we're going to talk about continuous random variables today. We'll talk about something called the uniform distribution and the normal distribution a little bit. We'll continue with that next week. And then actually on the 7th was originally scheduled to be our midterm. We were going to take it during class. So I'm just going to give it as a take-home assignment. And the midterm will be on everything from weeks 1 to 6. All right, but I'm actually going to start lecturing on a new topic the 7th because I originally going to lecture on that on the 8th, on week 8, I mean. So I'm going to lecture on a topic on the 13th called the central limit theorem, but that will not actually be on your midterm. So on week 7, what you'll do is you'll have your midterm assignment to do take home, and then you'll also have a post-class assignment on the central limit theorem. So it'll be a little bit of a heavy week, but I'll leave them both open for roughly, I'll leave the midterm open for a week and this assignment open for 2 weeks so that you could do it on the week I'm not here. Does that make sense to everybody?
Sounds good.
All right, and then I'll talk about the midterm in more detail as we get a little bit closer, and how you'll submit it the same exact way you submitted your homework this time. So, and the midterm's nothing really to stress about. I get good vibes. I think everybody will do great. All right. Before I get started then, does anybody have any questions about so there was a question posted to me privately. Where are the recordings from? Are you talking about the live classes, like these classes here? Yeah, so let's see. Here we go. If you look in the classroom, there's this tab called Recorded Lectures. If you click there, here are all the lectures and the write-ups that I use for them. Does that answer your question? Yeah, no problem. No problem. All right, let me just say one quick thing about the midterm then. The midterm is going to be, I think it's 10 questions. I'm not sure. I forgot the exact number of questions. But the way I grade the midterm is you submit like your best 5 questions or your best 6 or 7 questions out of the 10, and I grade those. So if there's some topics that give you a little bit of trouble, you can actually skip those on the midterm. Like for example, from last week, one of the things that students tend to struggle with a little bit is this binomial probability distribution. So there's a question of that on the midterm, but since there's like 10 questions and you only have to answer 7, if you're like, that question gave me trouble, you can skip it. All right, does that make sense as well? Put people's mind a little bit at ease about the midterm.
So we only have to answer 7?
Yeah, so what'll happen is the midterm, it'll be like, it might be less than 10 questions, forgive me. But what'll happen will be, there'll be 10 questions on there. And I'll grade your best 7, okay? So there, you'll get a question related basically to each week or each major topic of the class. So like there'll be a question on descriptive statistics, probability, regression, the discrete random variables, what we talk about today, what we talk about next week. And there'll be all different types of questions, and I'll only grade your best 7. Okay, so if there's one topic over the last, first half of the class that gives you trouble, you can skip that question on the midterm. Make sense?
Yes.
Yep.
Okay. And the final exam's the same way. Okay. One thing about it is if you answer more than 7 questions, I'll still just, like if you answer 8 or 9 or 10 of them, which you should try to do, I'll just grade your best 7. So there's no downside to trying to answer more than 7 questions on the midterm. Okay. And I'll grade your week 4 homework sometime this week. Just give me a couple days to get your grades in. I'll try to get them in today, but we'll see. All right. If there's no other questions, then why don't we get started? So today, the course actually seems to change a little bit. The topics seem a little bit different than before, and this is kind of where we begin our advanced study of the topics of this class. And we're going to talk a lot about probability distributions today, next week, and even the week after. Okay, it's like we're going to spend 3 weeks on this concept of probability distributions. So today's talking about the uniform and normal probability distributions. Okay, so what's the deal with this section? Like what's going on? So in this section, what we want to do is we want to apply the concepts of what we call a probability distribution, okay? And you learned about this last week in the post-class lectures, but don't worry, I'll do a review of this. To continuous random variables. Okay, so just recall. All right, what is a random variable in statistics? Okay, so all it is, it's the numerical outcome or measure, or let me just say numerical measure for the outcome of a probability experiment. Okay, so last week on your own, what we talked about was these things called discrete random variables. All right, the most common discrete random variable is what letter in mathematics, I just gave it away. What letter in mathematics do we use to represent a variable generally? All right, thank you. Yes, X. I haven't had enough coffee yet today, sorry. All right, I tried giving up coffee for a week, it didn't go so well. All right, so I'm gonna let X be equal to the result on a die roll. Okay, we say this is a discrete random variable, okay, because there's a finite number of outcomes. So X could be the values 1, 2, 3, 4, 5, or 6, okay? So this week, and going forward, basically the rest of the class just deals with continuous random variables, okay? So when you see the word continuous, have we talked about that before in this class? A continuous variable? You got to think back way to like the first lecture.
Yeah, it's like infinite number. It could be like decimals.
Yep. Okay. So what it is it's a measurement of some type. Okay. Yep. And an infinite number of possible outcomes. Okay. So how you work with probability distributions for continuous random variables is like very different than how you do it for discrete probability distributions. Like if you remember, a discrete probability distribution was just a table. It listed X and it listed their corresponding probabilities. You know, like this was the probability distribution for a die roll. Okay. How we do this for continuous random variables is way different, okay? We use what are called curves. They'll actually be called density curves. I'll talk about that in a bit. more than tables. We won't use these tables anymore. Okay, so it's a little bit harder concept. Okay. So now let me just say a few things as we go through this lecture. This lecture at first, there's going to be a lot of weird definitions and stuff, and it's going to seem super confusing, but just let me get through the definitions. And I promise you that after we do the definitions and stuff, when we do 1 or 2 examples, it makes sense. Like, it's just like, oh, okay, now I get what he meant by this definition and this definition. So just bear with me as we work through it, okay? All right, so this is the example we're going to use today to help us understand the definitions or the initial concepts, okay? So keep this example in your mind throughout the class today, and this is the example. Suppose the United Parcel Service, so UPS, is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Okay, so we're going to just assume for this the package will come between 10 a.m. and 11 a.m. Okay, we're going to assume that they're correct, okay? But so now here's the thing. Suppose it's this package like I really want to get, okay? And so like I don't want to wait, you know, I'm going to like count how long I have to wait for it, okay? Just kind of a sidebar. I don't know if anybody like at home quarantine, I find myself just buying more stuff off the internet than I ever did before, just because I have more time to just sit at home. Has anybody ever noticed that about the quarantine over the last few months?
Yeah.
Definitely.
Yeah. I get like an Amazon or a Target package every day. And then usually like a week later, I'm like, why did I buy that? It's just, there's no use for it. But anyways. So we're going to count how much time I spend waiting. So we're going to let this variable X, okay, represent, yes, quarantine plus a newborn. Actually, another sidebar, my wife actually does all the newborn buying, which is really great. So every week we get like, she shows off a new book or a new onesie. It's really cute. Anyways, so we're going to let this random variable X represent the time from 10 a.m. when the delivery is supposed to take place. So I'm going to let X equal to the time spent waiting for the package. Okay. So just to make this easy, I'll record this in minutes. Okay. So if the delivery comes right at 10 a.m., okay, so they said, hey, I'm going to come between 10 a.m. and 11 a.m. I waited 0 minutes. Okay. But if the outcome comes at 11 a.m., okay, I waited an hour for the package. So X is equal to 60 minutes. Okay. We're going to assume, all right, all 1 minute intervals between X is equal to 0 minutes and 60 minutes are equally likely. Okay. What I mean by that, if we assume that, is we're going to say that your package is just as likely to arrive between 10:15 and 6:15 as it is between 10:40 and 10:41. Okay, when I say something is equally likely over all intervals, this is going to be what's called, and I'm going to talk about this in more detail later, a uniform distribution. Okay, so first off, this is incredibly important. Does it make sense how I'm going to count the number of minutes that I spend waiting for my package? And that's what X is going to be equal to. So like if they say that they're going to come between 10 and 11, it's a random variable because I don't know how long I'm going to wait. Okay. Okay, does that make sense initially?
Yeah.
I got one yeah. Okay, so let me ask you a question. All right. So I'm gonna sit on my front porch and I'm gonna be waiting for my package. And I'm gonna have this variable X be the number of minutes that I spend waiting for the package. So here's the question for the day, okay? What is the probability that the package arrives sometime between 10 a.m. and 10:30? Does anybody have a guess?
It's like half.
That's exactly right. How did you get half?
Well, because that's just half of the hour. So like half of the whole time, 10 to 11, instead it's just 10 to 10:30.
Okay, you're absolutely right. So it's probably arrives between 10 a.m. and 10:30. Okay, so our window, this is how this was solved. Okay, the window of wait time is 60 minutes. Okay, and to go from 10 to 10:30 is 30 minutes. For a 30-minute window. Well, look, it's just, well, the 30-minute window divided by the total number of minutes that I could possibly spend waiting. This is our answer, okay? Just in the chat, does that kind of make sense to everybody? That it's incredibly important to just get that right now. I hope so. Okay. So here's what I'm going to do. I'm going to take this, what I think is rather simple example. Okay. The probability that you wait somewhere between 0 and 30 minutes of the 60 total possible minutes. Okay. And I'm going to throw some crazy definitions at it and make it a lot harder to kind of set up the terminology for later on in the class. Okay. All right. So keep this example here in mind. And then I'm going to come back to it after I go through a few definitions here. All right, so some definitions. Just recall that our random variable, X, is a continuous random variable. Okay, why? Because we are measuring the time spent waiting. So the first definition we have is what's called a density curve. All right, and then this is the part where I said, like, just go with the definitions and then this will make sense later on, okay? So a density curve is a curve that represents the distribution of a continuous random variable. Okay, so a density curve basically shows how the random variable or how the random variable's outcomes are distributed across the probability experiment. All right, just for now in like layman terms, the density curve shows just the distribution of the possible outcomes. So the curve, we're gonna do a little bit of graphing here. And the way you're gonna interpret the curve is the higher the curve is when you graph it from the horizontal axis, the more likely that outcome is. The smaller the curve is or the closer the curve is to the horizontal axis, the less likely that outcome is, okay? So we have this concept of a density curve. It's gonna seem weird at first, but it'll make sense when we get to some examples. Now we have this thing called a probability distribution function. Okay, I'll call it a PDF. So whenever I say find the PDF, it's going to be this probability density function. And so a function in mathematics, what a function is, you're used to seeing it perhaps as this notation. How many people recall seeing this function notation from their math courses?
Yeah.
Yep.
Okay, so all a function is you input something and a function outputs an answer or outputs a result. Okay. So a probability density function is an equation used to compute probabilities for a continuous random variable. All right, so you've actually had a probability distribution function-ish in a in the lecture last week. So the binomial probability distribution was a distribution function that we used to compute probabilities for a discrete random variable. So this PDF now is what we use to compute probabilities for a continuous random variable. All right. The thing that's incredibly important about a probability distribution function, the first one here, the total area under the graph of the equation over all possible values of the random variable must equal 1. Okay, so the area under curve must be equal to 1. Now, in probability, what does 1 represent? So if you think about it in probability, 1 represents 100% of the outcomes. So here's what we're doing. We're going to relate area under the curve to probability. Okay. There's a few key concepts throughout class today, and this is one of them. Okay. We're going to relate going forward area under the curve to probability somehow. Okay. So some area under a curve is going to be equal to the probability of observing a value between two numbers. And I'll flesh that out as we go forward. And the second property is the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. What this means is the graph never goes below the horizontal axis. Okay, it never goes negative. Okay, so we have this equation now, okay? And this equation is going to be used to compute probabilities for continuous random variables, okay? And then we had this other definition called a density curve, all right, which represents the distribution of the continuous random variable. So how is this concept of a density curve related to a probability density function? Well, the density curve is the graphical representation of the probability density function. So if you're given a PDF, remember that's just a mathematical equation. All right, what you're going to do is you're going to sketch the graph of this equation. And that resulting graph is called a density curve. Okay. How many people, just out of curiosity, I know this is a little confusing and it's like drinking from a fire hydrant, but how many people are like, I'm like a little confused what's going on, and how many people kind of like, I'm with you. So let me say, how many people this is kind of making sense, or how many people are like a little confused in the chat?
I am.
Yep. I'll be honest with you. I remember learning about this stuff as an undergrad, and being like, what are you talking about, professor? So I promise you, as soon as you see the first example, it begins to make sense, okay? It begins to make sense.
I mean, I took stat 3 times, so I kind of get it.
I'm not, we'll make sure this is your last one, okay? All right.
Hope so.
Yeah. All right. Okay, so how are we going to use these density curves in PDFs? Okay, so the first thing, this is how it's going to work. I'm going to give you some information, okay? And we're going to take that information and you're either going to be given the PDF or you'll find it. So generally for this first example that we're going to do, I'm going to give you some information and we'll find the probability density function, the mathematical equation. Super easy. And then once we have an equation, we're going to sketch it, okay? Then we're going to sketch the curve. So start with equation. Then sketch that equation. Okay. Second, what's going to happen is the area under the graph of that curve, the density function, okay, the curve, over an interval represents the probability of observing a value of a random variable in that interval. Okay. So this is the key concept from today's lecture. Okay. The area under the curve between two values is equal to the probability the random variable x falls between those two values. So the key concept is area under the curve represents the probability. And there's a little bit more to that, but that's just like in layman's terms. Just area under the curve is the probability. So let me go back and just try to like explain this here using our simple example here, okay? The total time, okay? Just imagine, this isn't exactly how it'll work, but just imagine like the total number of possible minutes you can spend waiting is between 0 and 60 minutes, okay? So think about, this isn't exactly how it's gonna work, but think about like, that means there's 60 possible values, okay? That's not exactly how it works, but. And then we're gonna ask you if you're gonna wait between 0 and 30 minutes, okay? Well, that's half of the possible values. So think about it as half of the area. So if we can find what half of the area is, boom, right there, that's the answer. And that's exactly what we're gonna be doing here, okay? So I wanna take this simple example, okay, waiting for a package at UPS, for UPS to deliver, and define what the density curve is for it, define what the probability distribution is, and then show you how area under the curve represents the probability. So if it seemed a little confusing at this point, like pay super attention, okay? Because this, what I'm going to talk about next is on your homework for the week. Okay, so let's go back and do this example. So the random variable x can be, so remember, I'm going to define it here. We're going to let x be equal to the time spent waiting for the package. Okay. And actually just kind of a little bit funny, you guys might laugh at this. While I was lecturing, I got a notice on my phone that I bought something on eBay and it's like, your package has been updated for delivery. So kind of a very appropriate example for me this morning. Okay. So the package said it was going to arrive between 10 a.m. and 11 a.m. Okay, and we're gonna measure this in minutes. Okay, so what is the least amount of time? And you help me in the chat here. What is the least amount of time that I can spend waiting for my package to arrive? Okay, yep. What's the most amount of time I can spend waiting for my package?
60.
Okay. So X is going to fall. It's going to be greater than or equal to 0, but less than or equal to 60. So think of this 0 as the starting value. And think of this 60 as the ending value. Okay. Now, because any two intervals of equal length between 0 and 60, okay, inclusive, are equally likely, what we say then, when intervals of equal length, all right, are equally likely, we say that X follows this uniform probability distribution. Now, this uniform probability distribution, okay, is going to be your first introduction to a density curve and a PDF, okay? So now what I want to do is I want to tell you what the formulas are for and what the formula is for the PDF of a uniform probability distribution, and then what its density curve looks like, okay? Okay, so what is the PDF for a uniform distribution? Okay, so it gets this f of x notation, okay? Now, I'm just curious, how many people from their algebra class remember what a piecewise defined function is? Okay, so all a piecewise defined function is, it just means that it has different mathematical equations for different values of input. So it looks like this. Okay, gets these special bracket bracers. And it's equal to two equations. It's equal to 1 divided by b minus a, and I'll explain what those are, for a less than or equal to x less than or equal to b, and 0 otherwise. Okay? So think of, this is important, a, think of a as the starting value, and b is equal to the ending value. Okay? Thinking about the previous example, okay? Did I give you a starting value and an ending value in the previous example?
Yes.
Yes.
I did, right? Right? So I gave you 0 is the starting, 60 is the ending. Okay, so you can see the B and A right here. Okay, so this function is only valid, it's only equal to a number between the possible values. Once you're outside, so once you're below 0 or once you're above 60, the function just says 0, can't happen. 0, can't happen. So what does the density curve for this look like? Well, it's super easy. You're just going to draw the first quadrant of the Cartesian plane, okay? Along the horizontal axis, you're going to put x, okay? All right, which is the random variable. And what goes along this vertical axis is f of x. All right, and think about this as the probability. So for any of these, what you're going to do is you're going to go, all right, what is my starting value? A. What is my ending value? B. And so when you go to graph between A and B, whenever x is between A and B, the value is 1 over B minus A. So 1 over B minus A. So between A and B, it's literally just this horizontal line. And then when you're outside of this, it's equal to 0.
Can you repeat that?
Sure. Whenever you're between A and B here, what I'm saying here is when X, so when your input X is between the values A and B,
Mm-hmm.
the value of the function is 1 over B minus A. So 1 over B minus A will be a number here.
Right.
And then you're just going to draw this horizontal line. Okay?
Okay.
And then when you're outside of it, so when you're less than A or greater than B,
Mm-hmm.
just equal to 0. So,
Okay.
and this graph will make more sense when we do, when I apply this to our example. Okay, trust me.
Okay. Thank you.
Yep. So I've got this super simple curve. Okay. It's just a horizontal line. Boom. That's it. Okay. And I've got this super simple function up here. All right. So now keep this in mind and I'll go back to it. But for our example today, let's do the PDF for a random variable X and let's do the density curve for a random variable X. Okay, so what I want to do now is instead of just having these like B minus A, A, B here, I want to actually put numbers to it, okay? So we let X be equal to the minutes spent waiting. And we knew that it was between 0 and 60. Okay, so if you look back here, I'm giving you A and I'm giving you B, the starting value and the ending value. So this is my A and this is my B. So my probability density function for this is equal to 1 over B minus A. So it's what minus what?
60 minus 0.
1 over 60 minus 0. This is 4, 0 less than or equal to X, less than or equal to 60. And it's 0 otherwise. So you can simplify this to just be 1 over 60 instead of writing 60 minus 0, okay? I actually think that's easier, so just writing it as 1 over 60, but I just wanted you to see it right there. Okay, so this is the equation we're going to use now to sketch our density curve. Okay, so X here, the random variable, is the time spent waiting. Okay, and up here, we're going to put f of X, which is our probability. All right, what's my starting value here?
0.
Okay, so I'm going to start at 0. What's my ending value?
60.
Okay, so this is not drawn to scale, okay? And then the possible values is 1 over 60. And then you're just going to literally draw a horizontal line. And then once you're outside of it, it's just 0. And it's just 0 here. And that's it. Okay. So let me ask you this. I know it was a little confusing, but does it kind of make sense now a little bit? At least plugging the numbers into the equation, does that make sense?
Yes.
Yeah.
All right. Now, I'm going to take this question that we knew the answer to, okay? What is the probability that a package arrives sometimes between 10 a.m. and 10:30 and relate it to all of this right here, okay? Okay, so here's how we're gonna write these problems or solve them. I ask you for a probability, okay? So we're gonna let X be equal to the time spent waiting. And I wanna find the probability, okay? So if it arrives between 10 a.m., you spend 0 minutes waiting. And if it arrives at 10:30, you spend 30 minutes waiting, okay? So I want to find the probability that X is somewhere between 0 and 30, okay? And if you look back, the key concept, I'm somehow going to relate area under the curve to be the answer to this question. So you're going to solve this, you're going to sketch the density curve. Okay, that's the first thing you're going to do. So I'm just going to re-sketch the density curve. Whoosh. Complete with sound effects there. And really what you don't have to do is you don't have to draw the zero stuff. You really just have to draw this, okay? Then the next thing you're going to do is you're going to shade in the area under the curve between the two values of interest. So I'm interested between 0 and then here's 30. So what I'm going to do is I'm going to shade in this area here under the curve, okay? That area that I just shaded in is the probability you're looking for. So you know what I just shaded in? I just shaded in a rectangle. It looks like a square, but it's actually a rectangle, okay? So how do you find the area of a rectangle? It's what times what?
Length times width.
Yep. So this probability is just equal to length times width. Well, the length of this rectangle is from here to here. So the length goes from 0 to 30. So the length is 30. The width goes from 0 to 1 over 60. So it's 30 times 1 over 60. Well, you know, if it helps, you can see 30 as 30 over 1. So this is just 30 over 60, which is exactly what we thought before. So do you see how I use the area there under the curve to find this probability?
Yes.
Okay. So obviously this was a super simple example for this one, okay? Let's do another one, okay? Let's do another problem. All right, just kind of the same question here, okay? So what is the probability that your package arrives sometime between 10:30 and 10:45? Okay, so again, X is going to be the time spent waiting. Okay. If the package shows up at 10:30, how long did I spend waiting?
30 minutes.
Okay. If it shows up at 10:45, how long did I spend waiting?
45.
Okay. So I want to find the probability that I spend waiting between 30 and 45 minutes. okay? So to do this, remember, just follow the steps. Sketch the density curve. Well, we know the density curve was this. Started at 0, went to 60. We knew the probability was 1 over 60. And then it's just a horizontal line. Next, you're going to shade in the area but under the curve between the two values of interest. Well, my two values of interest are 30 and 45. So here's 30, here's 45. I got to find this rectangle here, the area of this rectangle. Okay, so
Professor, question, sorry.
of course.
So is it always gonna be on the y-axis 1 over 60, or this is because of the example that you are giving us that it's
So
time-wise?
1 over 60 will change, okay?
Right, okay,
And so won't the possible values of x. Like I have another
Right.
example next where
okay,
everything changes, so you can see it
Mhm.
differently.
okay,
But
perfect,
it just depends on the problem. But the graph will
Got it.
always just be a horizontal line.
okay. Thank you.
Yeah. So next, find that area that you're looking for. Okay. So the area of that rectangle is just length times width. So the length, what is the length from 30 to 45?
15.
Yep. So it's just 15. And the width stays the same. So multiplying this is just 15 over 60, or 0.25. Make sense?
Yeah.
Ish. All right, so just a quick note on this before we do the second example. Probabilities will only be computed over an interval. All right, like if I ask you the question, what's the probability that the person shows up at exactly 10:30? So exactly as soon as my clock hits 10:30, the person's on my doorstep. So it's a probability that you wait exactly 30 minutes. Well, if you were to sketch this graph, that would be what the graph looks like. X is equal to 30. Well, you can't actually find the area under this, right? Because what's length times width here? What's the length of a line? It's not 1. So these probabilities for these continuous random variables, when I say what's the probability, it's exactly this value. It's actually not it's non-zero, but it's so close to 0, we just say the answer is 0. So we're only going to compute probabilities over an interval for all of these type of questions. Okay. All right. How about we do, before we take our break, let's do one more quick example. Does that sound okay?
Sounds good to me.
All right. And this example here, someone asked a great question, like is it always 0 to 60 and then 1 over 60? No, it always depends on the problem. Okay. So this was a question I asked on a midterm a few years ago. Okay, so you can see how this is done, okay? So suppose the travel time from White Plains Transit Center to SUNY WCC on public transit. So just out of curiosity, has anyone taken bus route number 40 before?
I have, but it was a long
Yes.
time ago.
I love
Yeah, me
public
too.
transit personally. Like if it wasn't a 3-hour public transit drive from my house to work, like if it was an hour and a half to 2 hours, I would take it every day. So, every once in a while I still do it, and I always get on the number 40 bus, okay? I think I could take the 38, I'm not sure, but I always get on the 40. Okay, anyways. So the travel time from the White Plains Transit Center to SUNY WCC on public transit follows a uniform distribution. Okay, so whenever you see that, okay, that uniform distribution stuff, all right, that's telling you it's going to be exactly like the problem we just did. With a minimum time, so the shortest it can take, like if there's no traffic, 12 minutes, and a maximum time of 22 minutes, okay? So just kind of seeing here, did I give you a starting value and an ending value here?
Yes.
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 Yep, so you can see how this is done, right? So this is my starting value. And this is my ending value. Okay, so I'm right there, boom, I'm giving you the A and B, okay? So let's let the random variable X represent the time from White Plains Transit Center to SUNY WCC on public transit. Okay, so I'm gonna let the random variable X here, okay, be the time spent on the bus. Okay, because it's time spent on a bus, this is a continuous random variable. And again, what is the least amount of time you can spend on the bus?
12 minutes.
Okay. And what's the most amount of time?
22 minutes.
Yep. Okay. So I'm giving you the, hey, look at that. That's crazy. I'm giving you the A and B, and I'm telling you it's uniform distribution. Okay. So now let's answer some questions, okay? What is the probability density function PDF for the random variable? Okay. So just recall, whenever you're given a uniform distribution, the probability density function is 1 over B minus A for X between A over B and 0 otherwise. So for our problem, what were A and B again?
22 and
12 and 22.
Yep, thank you. So it's 1 over 22 minus 12 for A less than, or for 12 less than or equal to X less than or equal to 22 and 0 otherwise. I'm going to clean this up a little bit. Okay. What's 22 minus 12?
10. 1 over 10.
So 1 over 10. All right. For values of 12 less than or equal to X less than or equal to 22, 0 otherwise. So you can see already how this is changing from the previous example, right? Like the previous example was 0 to 60, 1 over 60. This is 1 over 10, 12 to 22. So it's just like straight up just applying the information you're given to the formula. All right, sketch the density curve. So just recall the density curve for any problem that's uniform distribution is just a horizontal line that looks like this. Okay, A and B, 1 over B minus A. So for our problem, and remember just f of x, or x is the time on bus, and f of x, here's the probability. What is my value of A again?
12.
What's my value of B?
22.
And 1 over B minus A is?
1 over 10.
And I'm just going to draw this horizontal line. Okay. So now the question is, what is the probability that the travel time okay, is between 15 and 18 minutes. So somewhere between the time I spend on the bus is 15 minutes to 18 minutes. So I want to find the probability that my X variable is between 15 and 18 minutes. So what you do is you go back to your density curve. You go to 15. You mark off where 18 is. And you shade the area under the curve to find this probability. So again, for these uniform distributions, it's just length times width. Well, what is the length from 15 to 18?
3.
3.
3.
Okay. And what is the width?
1/10.
3 times 1 over 10 is 3/10, or 0.30. So like notice how quickly that problem is done when you know exactly what you're looking for. Okay. I realize how ridiculous that statement just says. Obviously, if you know exactly what you're looking for, it should be an easy problem. But like, having seen me do a second example, does this kind of make sense?
Yeah.
Yes.
Yes.
Do you think you could handle one of these? I know only a few people are answering, but like there'll be a question like this, exactly like this on the midterm. Okay. I would not skip this problem on the midterm. Okay. Because it's a take home at midterm, like the only thing that's going to change is the numbers, but how you tackle this problem will be exactly the same. Okay. I think you guys could do this problem.
100%.
That's not bad. I agree. It's not bad. It's not the best. It's not the worst. Okay, so it's 9:57. Let's take a 5-minute break. Let's come back. Let's start back. Let's start back at let's just say 10:03. All right, everybody sound good?
Yep.
All right, I'll see everybody in 5 minutes. All right, let's finish up for the morning. So okay, everybody can hear me again? Everybody okay with the sound?
Yep.
Yes.
Yes.
Okay, so the uniform distribution, I'll be honest, we won't actually talk about again in the class. You'll get a question about it on the midterm, but what the uniform distribution does is it helps us introduce terminology like a density curve and a probability density function that we're going to use for a different distribution. So what I'm going to do in class now is I'm going to talk about something called the normal distribution. And just to go back into the week 5 tab here. So under your post-class requirements, the lecture you should watch here after class is this one here, Introduction to the Normal Distribution. So there's this page here. And what I have here is this first video just kind of like redoes what I've talked about with the uniform distribution, introduces the normal distribution. And then this second video shows applications from the week. So your homework assignment this week under week 5 is an online quiz again where you get 2 attempts. And it's going to cover the uniform distribution, which is what I talked about for the first hour. And then literally what I'm going to talk about for the next hour, next 45 minutes or so. And then this video here, okay? If you're interested, just as a little advanced under this post-class lecture here, this lecture is optional, but if you just are, I don't know, bored during the week and want to work ahead, this is a kind of an introduction to what I'm going to be covering next week. Okay. All right. So the uniform distribution is not often used in the real world. There's not just too many applications to this. So a more common distribution that is a naturally occurring distribution and that shows up in statistics a ton is this thing called the normal distribution. So you're going to hear me use a bunch of things interchangeably. I'll say something like the normal curve instead of normal distribution, or I'll say the bell curve. But it's a distribution that looks like this. Okay, this is what the curve looks like. How many people have seen this type of bell curve before?
Well,
Yep.
Yes. What we're going to do is we're going to study the normal distribution literally for the next 3 weeks. There's a ton of great applications to it, some very interesting statistical theories behind it, because it's the foundation for all of our advanced study. Okay, so this week I'm going to show you how to do a lot of problems by hand, but next week you'll notice we didn't really use our calculator today. Next week, please have your graphing calculator handy because we're going to use it a ton. Okay, so a continuous random variable, all right, x is normally distributed. So when I say normally distributed, it means it follows that bell curve shape. If it's frequency histogram, so if you look at the histogram, so remember a histogram are things that look like this, all right, has the shape of a normal curve. So if the histogram like this kind of looks like this bell curve, all right, we just say, oh, hey, the random variable x just follows this normal distribution, this bell curve. So like, let me give you just an example of this, okay? So here we have this histogram, all right, and it looks like it's centered, the high point of the graph occurs at whatever number 100, okay? And then as you move to the right from the center, the histogram falls and falls and falls. And then as you move to the left from the center, the histogram falls and falls and falls, okay? So things like this, even though it's not perfect, frequency histograms that are symmetric like this and bell-shaped, this is how you know it has the shape of a normal curve. So we say this variable is normally distributed. Okay, so that's just like if you're given a data set, how you would look to see if it's normally distributed. Okay, but in this class, I will often just tell you it's normally distributed. I'll often say something like the variable is normally distributed. Just to go back, like if you look in this example here, you know, what I told you was I say, hey, it follows a normal, okay. Oh, can you guys hear my kid in the background? Is that why you said that? Yeah, yeah. So sorry, you know, it's nap time actually. Yeah, I have an excuse. I have to be doing my job. So my beautiful wife and mother-in-law are here today taking care of the kid. So, you know, sorry about that. It sounds like he went down. Nope, spoke too soon. Spoke too soon. The joys of parenthood, you know. Actually, it's great. I don't know how many people on the call have kids, but having a kid is great. It's awesome. Thank you. I appreciate that. I appreciate you guys saying it's all okay. I'm looking forward to when he gets a little bit older, although I'm nervous. I know I'm on a sidebar here, but yeah, we're putting him in daycare in January. So I'm a little nervous about that. But you know, we'll see how it goes. All right. Anyways, so the terrible twos. Yeah, I've heard about those. So go back to this. So when a problem like this one, I'll tell you, I say it follows a uniform distribution. For problems going forward, what I'll often say is like, oh, this variable follows a normal distribution. And so that'll tell you whenever I say, hey, it follows a normal distribution, you'll use the properties that I'm going to talk about in the coming slides. Okay. All right. So when a random variable is normally distributed, all right, we can model the variable using what's called the normal density curve. Okay. So just remember like how we had the uniform. It just looked like a horizontal line. Okay. This one gets a little bit harder. Okay. This one, the density curve is going to look at, it's going to follow this bell-shaped curve. Okay. Does anybody remember what this Greek letter stands for? I guess I have it right here. It stands for the population. Yep. So the curve is centered around whatever the mean is, the average for that random variable. And the probability is not uniform. Like if you notice area under the curve, there's more area under the curve closer to the average than there is away from the average. Okay. So we're going to be using this type of curve now, but we're going to solve the same way. We're going to shade some area under the curve and find that area. Okay. The equation. Okay. So that's just what the density curve looks like. The normal PDF, the probability density function. Okay. So remember for the uniform distribution, it was real simple. Okay. This is what the distribution or the probability density function looks like. So just remember X is our variable. All right. You're going to need to use this equation. You're going to need to know the average. You're going to need to know the standard deviation. All right. For the variable, and it's just equal to 1 divided by the square root of 2 pi times the standard deviation squared or the variance times E, and then E is all raised to this power. Okay. Does this equation look easy to work with?
Not at first.
All right, the answer
Not
is
much, but
the
yeah.
answer is this equation looks terrible. Okay.
Yes.
So actually, to even be able to use this equation to find the area under the curve, you'd actually need to use calculus. So it's you know, I would get questions like this in graduate school, okay? So I just wanted to put this equation here, I always do, to note that like this uniform curve had an equation behind it. This bell curve also has an equation behind it, and this is the equation, okay? But the good news is the equation is scary, but don't worry, we'll never use it again. All right, so we're gonna work problems using 3 different ways, okay? So with the time we have left in class, we're gonna talk about how you use graphs and the properties of the normal curve to answer probability questions. All right, next class, I'm gonna show you these 2. Next class, I'm going to show you how to use a statistical table. So you'll learn how to read your first statistical table. It's incredibly easy. Don't stress about it. So we'll do problems by hand a bunch, just so you can see what's going on. And then I'm going to show you how to use your graphing calculator. Like, do you guys remember when we did regression? I showed you how to do it by hand. And then I said, oh, okay, well, you know what? There's actually an easier way with your graphing calculator. So that's what we'll do at the end of class next time. Okay, and then just like with regression, you can use your graphing calculator for all the problems. Okay, so your homework this week though asks you to solve using the properties of the normal curve. So this is on the homework this week. And the properties at first seem a little confusing, but they're actually not that bad. Okay, so just remember, there's an equation for this, but this is what the density curve looks like. Okay, and just remember the key concept. Area under the curve is the probability. Okay, so here are the properties of this normal density curve that we're going to use to help us answer some probability questions. Okay, the first one is the curve is symmetric about the mean. So when you sketch the curve, the curve is symmetric or centered around this guy, the mean, whatever the mean is for the variable. What does something mean when I say the curve is symmetric?
It's like equal on both sides.
Yep.
Like it rises the same rate as it falls.
On both sides. That's exactly right. Thank you. Yeah. So what symmetric means, if I were to take this curve and like cut it in half and fold the sides on top of each other, they would match. They would be mirrors of each other. That's what symmetric means. So on either side of the average, the curves are exactly the same. All right. So when something's normally distributed, all right, the key feature here is that the mean is equal to the median is equal to the mode. So those 3 measures of central tendency are the same. So this curve has a single peak to it, all right? And the highest point of the curve occurs when x is equal to the mean. So the high point of the curve here occurs at the average, okay? So when you sketch this, when you get to the average, that's the high point, you're gonna fall back down. All right, the area under the curve is 1, just like it is for all density curves. The total area under the curve is 1, all right? That's how we relate it to probability. And then because the curve is symmetric, the area under the curve to the right of the average is equal to the area under the curve to the left of the average. So what I mean is half the area is above the mean and half is below. All right, and then total area is 1. Okay, always, always, always. The next one as x increases without bound, right, that means as x gets larger and larger and larger, the graph approaches but never actually reaches the horizontal axis. So what that means is there's an asymptote at the horizontal axis, and it's the same thing as x decreases, okay? So what this means is x, the value of your random variable x increases, right? This graph gets closer and closer and closer and closer and closer and closer to the bottom, but never touches it. And it's the same thing over here. It gets closer and closer and closer, closer to the horizontal axis, but never touches it. Okay, and this is across all possible values of x. And then this is the next thing, and this is what we're going to spend the most important on today, the empirical rule. So this was really briefly covered, okay, on your first post-class assignment or your first post-class lectures. When something follows the normal distribution, this empirical rule holds, okay? So approximately 68% of the area under the normal curve is between, if you take the mean and you subtract one standard deviation, to the mean plus the standard deviation. And don't worry, I'm going to show a visual of this next, okay? Next, approximately 95% of the area is between, if you take the mean and subtract 2 standard deviations, and you take the mean and add 2 standard deviations. And then finally, approximately 99.7% of the area is between the mean minus 3 standard deviations and the mean plus 3 standard deviations. Okay, so you can see obviously that when something's normally distributed, 99.7% of observations are within 3 standard deviations on either side of the average. Okay, that's just important to know. All right, let me show you the visual of this empirical rule, okay? And this right here is the most important slide that you can have today. Like when you go to do your homework, okay? If you just have this slide here, you'll be able to answer most of the questions like incredibly easily, all right? Right, and we're gonna get through one example of this so you can see how it relates to your homework, okay? So whatever the mean is, if you add 1 standard deviation to it and you subtract 1 standard deviation to it, 68% of the area falls. And you can see it's right here in this teal color. Because the curve is symmetric, that means 34% of this curve's area falls from here to here, and 34% falls from here to here. So just changing it to a decimal, it's just like that. If you go out another standard deviation on each side, 95% of area falls from here to here, and you can see it up here, okay? Similarly, all right, because it's 95%, I have it broken down into 2 separate categories, but from here all the way to here is 47.5% of the area, and from here all the way to here is 47.5% of the area, because all I'm doing is taking 95% and dividing it by 2 because it's symmetric. And then you can go out more. You can go out 3 standard deviations, like this. And at that point, you get 99.7% of the area. Okay? This visual right here is how we're going to answer all of our application problems initially, okay? So let me just do talk about one other thing, and then I'll show you an example. And just like with the uniform distribution, I think, you know, once you see an example of how this stuff is applied, I think this graph will end up making sense. All right, one thing about normal curves, and this is important, not all normal curves look the same. Okay, just like how not all uniform curves look the same. Like, let me just go back for a second real quickly. This uniform curve here, 1 over 10, 12 to 22, looks different than 0 to 60, 1 over 60. Okay, they're both horizontal lines, right? But like the length and width of both of these two curves were different. Okay, so it's the same thing for a normal distribution. Okay, the basic bell curve shape is the same. Okay, but the curves will look different. So like here's one curve that has a mean of 0 and standard deviation of 1. Here's a curve that has a mean of 3 and standard deviation of 1. Like the curves are centered at different points, but they look the same. Okay, but they're centered at different values. This one's centered at 0, and this one's centered at 3. This one here, this illustrates the difference between when the standard deviations look different. Both of these curves, the curve in pink here is centered at 0, and this curve in, I guess, turquoise is centered at 0. But this curve has a standard deviation of 1. And this curve has a standard deviation of 2. A smaller standard deviation means the curve is taller. A larger standard deviation means the curve is shorter and wider. Okay, but they both maintain this bell-shaped curve. Like you can still see that curve here. Okay. All right, what do you think? We end class now. I know I went through this pretty quickly with an example of this normal distribution and normal density curve. Okay, sound like a good way to end it?
Professor, I have
Yeah.
a question. Can you just repeat that? You said a smaller standard deviation curve is taller, and then,
Yep, I'll write it down, okay?
thank you.
Yep. When comparing curves, okay, and this is centered at the same value. Like here, they're both centered at 0. Okay.
Mhm.
A smaller standard deviation means the curve is taller. And I guess I hate to use these terminology, not skinnier, but is taller and more compact. Like you can see that like the curve, it looks, the distances here are closer together, okay?
Mm.
A larger standard deviation means the curve is shorter and less compact. Like you can see here, this one that has a standard deviation of 2, it's shorter and looks more spread out.
Mm-hmm.
Yeah, that's all it means. But they
Okay.
still both maintain the bell shape.
Okay, thank you.
Yeah. About to sneeze, give me a second. Oh, that's the worst feeling, right? When you feel like you can want to sneeze, but you can't.
True.
All right, so let's just do one example of this. And I promise you, actually, if you just pay attention to this example and remember the uniform example I did here, you'll be able to answer the homework questions, okay? And then the videos that are posted will just be a review for you. Okay, so here's the question. Suppose the talk time on the iPhone 10, okay? I actually have an iPhone 8, I'm an iPhone user, but let's just suppose talk time is normally distributed. Okay, so notice how I tell you it's normally distributed, so that's given. So whenever you see that, you're gonna use the bell curve, okay? With a mean, so let me just tell you what talk time is. Talk time is a measure of if you were to just turn your phone on and it was charged at 100% and just started talking, just called somebody and talked nonstop, how long you could talk before your phone dies, okay? So it's saying here that the mean, the average talk time, which is the Greek letter mu, is 20 hours. So you could talk 20 hours straight before your phone dies. And the standard deviation, which is the Greek letter sigma, is 5 hours. So let me ask you this. Do you think every iPhone 10 has exactly the same talk time? Like meaning they'll last exactly the same amount of time?
Probably not.
No, yeah, like there's a lot of things that could influence, right? Like how many apps you have on there, probably how much storage you have free. Gosh, how old your phone is. Like there's just a ton of things that can mess with the talk time. Okay, so what we're just saying is, well, look, not all phones get the same amount of talk time, but the talk time ends up being normally distributed across all phones. On average, phones get 10 hours of talk time, and the standard deviation is 5 hours. Okay. So suppose I'm interested in answering some questions or studying talk time. So what I'm going to do is I'm going to take an iPhone 10 and I'm going to select it at random from all the iPhone 10s that are out there. And what I'm going to do is I'm going to run this experiment. I'm going to turn it, I'm going to charge it, and then I'm going to call somebody and I'm going to measure the talk time. Okay, like how long it takes until the phone dies. Okay. So before I select that talk time, or before I select that iPhone and record the talk time, do I know exactly how long the phone will last?
No.
Yeah. How long its talk time will be? You don't. No. So it's a random outcome. Okay. Right? Like, depends whose phone I select, it's just going to be a random outcome. So I'm going to define this variable. Okay. I'm going to let X be the talk time on a randomly selected iPhone 10. So I'm going to let X be the talk time on random iPhone 10. And now, is talk time a discrete or continuous variable? It's like time
Continuous.
Yep. So this is a continuous random variable. And this is what we know, and this is how I'll write things. When I say it is normally distributed, you'll see me do this notation. I'll say X, and this squiggly line tells me X follows or is approximately normally distributed. And I'll just write, again, the mean was 20 hours, and the standard deviation is 5 hours. So whenever we do these problems literally over the next 3 weeks, these 3 things will always be given to you. Okay, and when you see these 3 things, when I say, hey, it's normally distributed, the mean is 20 hours and the standard deviation is 5 hours, you're gonna be primed that, okay, it's a normal curve problem. I'm gonna solve it, using the methods Matt talked about, okay? So keep this in mind. X is normally distributed, mean is 20, standard deviation is 5 hours. Okay. Is X a discrete or continuous random variable? We already answered that. Now the next question says, sketch the density curve. Okay. Now I want to go back. this is what the density curve looks like. It looks like this bell-shaped curve, okay? So now we have to sketch this, all right? And for these very simple problems, what we're gonna do is we're gonna sketch it, and we're gonna sketch it using or identifying these key markers here, okay, for the empirical rule, okay? So what we're gonna do is we're gonna sketch the curve and center it around the mean, and then we're gonna add a standard deviation, add another one, and then we're gonna subtract a standard deviation, subtract another one, and then subtract another one. Okay, so the density curve here is the bell curve. So what you're gonna do is you're gonna sketch initially. Oh, this is terrible. The bell curve. Oh my gosh, that's so bad. I'm sorry. I'm gonna do a better job. I'm not sure that came out better, but all right. So you're gonna.
It looks good.
I'm sorry.
It looks good.
Thank you. It's
You are doing it with a mouse, right? So it's 10 times more difficult.
So actually, believe it or not, I'm actually not using a mouse.
Oh.
I'm using a little pen marker.
Oh, great.
Yeah.
Oh.
I couldn't imagine doing all this with a mouse, but it's literally a 6x6 pad. So, okay. Anyways, what you're going to do this, the high point of the graph, all right, occurs at the mean. Okay. So remember the mean was 20 hours. So you're going to mark here the number 20. All right. Now the standard deviation was 5 hours. So what you're going to do, going back, you're going to take the mean, you're going to add a standard deviation 3 times. So the first tick mark I get over here, I added 5, I got 25. What would be the next tick mark?
30.
30.
30,
And what's the next one, last one?
35.
Yep, and now I'm going to do it on the other side. So subtract a standard deviation, I get 15. Then what's the next one?
10.
10.
And then 5. Okay? And that's literally it right there. Okay? I'm not going to put the vertical axis on this anymore. Okay? We don't need it for this problem. Okay? You could put it there if you wanted, like if you wanted to go out to 0 and do this. But it's not really necessary anymore. Okay? Now that we got this, okay, here's the question. What is the probability that the talk time of a randomly selected iPhone is between 10 hours, so I can only talk for 10 hours, okay, and 25 hours? All right, so let me write it with as a probability statement. So the probability that you're between 10 and 25 hours, okay? So how are we gonna solve this, okay? I just wanna go back a few slides, okay, and then I'm gonna come back here. Whenever you have a density curve, sorry, I know I'm going fast. You're always gonna follow this method. You're gonna sketch the density curve. You're gonna shade in the area under the curve between the two values of interest. And then, you know, the trick was for the uniform distribution, you just use the area of a rectangle. For the normal curve, you're just gonna have to use some other trick to find the area. Okay, so what I'm gonna do is I'm just gonna quickly replicate the density curve so you can see it. Okay. So I want to be between 10. So here's 10 and 25. All right. So I want to find this area here to the left of 20. And I want to find this area here to the right of 20. And now what you're going to do to answer this is you're going to use that empirical rule, all right, which was number 6 to solve. Okay, so here's how I tackle these problems. To go from 20 to 25, okay, how many standard deviations is that?
1.
Okay. So you're going to look back on your curve on this one right here. To go from the mean to 1 standard deviation, what is the area under the curve between here and here?
0.34.
0.34.
Oh, okay.
So that means this first area here is 0.34. Now to go from 20 to 10, how many standard deviations is that?
3.
Not 3,
2.
2, yeah. Right, 1, 2 standard deviations, do you see that? So now you just go back to this chart here. So to go from the mean here to 2 standard deviations, from here to here, what did I say the area from here to here is?
47.5.
Yep, right there. It's 34% plus 13.5%. And just changing that to a decimal, got to change it to a decimal, is 0.475.
Okay.
So what should I do with these two numbers?
Add them.
Yep. What do you get when you do this? You get
0.815.
Yeah, thank you. I knew that.
I know you did.
Thank you. So that's your answer right there. Do you guys see how I used the empirical chart there to help me figure this out?
Yeah.
Yes.
Yeah, so what this is just, I'm going to do another example so you can see exactly what's going on here. But what's going on here is that instead of using like the length times width, because there's no like easy formula to find the area under this curve. That there was that crazy equation. So instead what we had to use was this empirical rule chart here. All right, let me do another one, okay? I got 9 minutes, okay. So the next question is, what is the probability that the talk time for a randomly selected iPhone 10 is between 25 and 30 hours? Okay. So what two values do I want to be between, my X to be between?
$25.
And 30. Sorry.
That's okay, that's okay.
Um,
All right, so I'm going to start by writing the probability statement. The next thing you do is you sketch the curve.
Okay.
So it's centered at 20, 25, 30, 35, 15, 10, and 5. And then what you do is you shade in the area you're interested in. So I'm interested between 25 and 30 right here. So this red area here, okay? So another way of thinking this is I'm interested in the area between 1 and 2 standard deviations from the mean. Okay, because to go from 20 to 25 is 1 standard deviation, and to go from 20 to 30 is 2 standard deviations. So literally, all you do is you go back to this chart and you say, okay, here's the mean to 1 standard deviation. Here's 2 standard deviations right here. What's the corresponding area right there?
13.5.
Yep. And you just change it to a decimal. Post in the chat if that made sense. I can't tell how many people are still paying attention. It's literally just drawing the curve, shading in the area you're interested in, and then using that chart to find it. So 20 is, someone asked, why is 20 in the middle? So that's the mean. So it's always centered around the mean. So if you look back at the problem, the mean was 20 and the standard deviation was 5. These two things will always be given. Okay. Does that answer your question? Always will be given. All right, let me just end on this last question. So what is the probability for a randomly selected iPhone 10, the talk time is more than 25 hours? Okay, so I want to find the probability that X is more than 25 hours here. So it's greater than or equal to 25. So actually the reality is, I didn't cover it too much in this lecture, but the equal signs don't matter for these type of problems. It's just because the probability of it being exactly 25, remember, is 0. So there is no difference between this. Okay, with the equal signs or not, it's still the same answer. Okay, so I just want the iPhone 10 to be greater than 25 hours. So let me draw the curve again. So 20, 15, 10, this is a terrible curve, but 25, 30, 35. Okay, so here's 25. Okay, so I want to be greater than 25. So I'm going to start shading. Okay. Do you think I stop at 35?
No.
Nope, nope, you keep going. Okay, so this is what's called a tail probability. So remember, only 99.7% of iPhones have talk time between 5 and 35. So there's still some talk times, not many, only a few, that have talk times greater than 35 minutes. So it's, you know, not that many, but there are a number there. So I have to figure out how to answer this problem. So I got to find this red shaded area here. And I have no idea how to do it. Anybody got a guess? I do know how to do it. I'm just guessing. Anybody?
Can you
Yeah,
just
so
look
you
at-
can assume that half, like 50%, is from the mean.
Perfect. Yep.
So then you would subtract that the middle space to the right of the mean. Yeah.
Which is
So
how
you
much?
know that is 0.34.
Perfect. Perfect. Yep. I'll finish it from here, but amazing job on that. So this is how we tackle these tail problems. All right. We know that the total area to the right of the mean is 0.5. But hey, I don't care about the people or the phones between 20 and 25. So if I don't care about it, I have to take it away. Okay. Well, how much do I have to take away? So you just go back to the chart and you say, okay, the middle, or to go from the mean to one standard deviation is 0.34. So I have to take that away. From the 0.5. And that's your answer right there. Okay, what do you, I'm button up, class is almost over. What did you guys think? Think it could handle some of this on the homework?
Yes.
Okay, I got some good news, bad news. The homework this week, these problems are actually kind of easy. Like what I'm gonna ask you in the future, so like next week, so you can see what's going on. What if I asked you the probability that a talk time is between 17 minutes and 21 minutes? Do you notice how like 17 and 21 don't fall on a nice standard deviation? So
Yes.
we're gonna need a different method, okay? So your homework this week will just be problems that use the empirical rule, but next week I'm gonna show you how, hey, what if it doesn't fall on a nice standard deviation? How do you tackle the problem? Okay.
With your calculator.
Yeah. All right, spoiler, yes, the answer will ultimately be with your calculator, but I'll show you how to do that with your calculator. That was funny. That was a good joke. You stole my joke. All right, everybody. So I'm going to post the recording in a little bit. Thanks for a great class. Do your homework. Can you guys still hear me okay?
Yes.
Yes.
Yeah, the
Yep.
PowerPoint froze there for a little bit. Yeah, shoot me an email if you have any questions. And I hope you guys enjoyed this lecture. I love teaching this lecture. I think it's super fun. I don't know if you could tell I was having a lot of fun. So next week will also be fun. All right, everybody. I'll catch you next week.
Thank you, Professor.
Thank you, Professor.
Thank
Thank
you.
you. Have a good
Thank
one.
you.
You, everybody, as well.